Hi, once again, this is Eli, and today we will be doing a physics lecture. This is the second one, and we will be covering kinematics, we'll be covering momentum, we will probably be covering energy. We will be covering energy, yes. And well, without further ado, let's get into it. So, as we begin, we will probably be starting with kinematics because that is usually the first thing that we learn, and it's something that'll be very, very useful later on. So we should start by deriving all of our kinematic equations. So starting here, I have them all written out so that we can see them nicely, and I won't have to, write them out since that takes a lot of time, and we don't want to keep you guys waiting. We have our main assumption of this unit of kinematics, that acceleration is constant. Acceleration is constant. What does that mean? Well, we know that we can think of it like this. We have displacement, right, which is just, I have a pen and it moves from here to here. It's been displaced this amount of distance. Now, while it's been displaced, it travels, right? So the speed in which it travels in units per second, that is its velocity. Usually it's in meters per second. Now, if it starts like this and it speeds up, it has a change in velocity. So in the same way that we have a change in displacement is velocity, a change in velocity is acceleration. That is, it's the rate at which velocity changes, right? So that's acceleration right here, right? As we see, it's the difference in v over the difference in t. Now, another way of saying difference in v is just saying the v final minus the v initial. So here's where we need to use a little bit of calculus intuition that we have. We have a v initial. It starts, say, for example, in this example, at rest. It slowly speeds up, right, until it gets to the end. So we want to know the instantaneous velocity as it is at its end. That will be its v final. So if we say v final minus v initial, that's how much the velocity has changed. That's that over time. Now, the first equation is very easy because we just rearrange that a little bit and we get that v final is equal to v initial plus acceleration times time. There we go. That's our first kinematic equation right there. Simple and easy. Now, for our second equation, we're going to use a little bit of a funner and more sophisticated derivation. We're going to use geometry. So what I have over here is a graph of velocity versus time. Now I've set a curve over here, so you can ignore all of this. All we see is this line, right? That's our velocity line. Notice, by the way, that it is increasing, and it's increasing linearly. Why is that? Well, because our assumption is that acceleration is constant. If you would see this line go crazy, acceleration is not constant, because an increase in velocity, that's acceleration, right? So we can see here that it's constant. Now, what I've done, you see it starts at v naught, and it goes all the way to v. V naught is just v initial. It's another way of saying, the v in the beginning. I've drawn a little line, a helping line here, so that we can calculate the area under the curve. Now, why would we want the area under the curve? Here's where also, again, calculus comes into play, because we know that that the integral, right, is the area under a curve. Now, if the curve here represents a function of velocity over time, then the overall velocity will have to be displacement, right? As I said that, I realized that may not be 100% clear. So why is it that the integral of a velocity function is displacement? Well, if we look up here, acceleration is equal to, by definition, right, the difference in v, right, over the difference in t. What if we take the integral of both sides with respect to t? Well, the difference in t would drop out, right? And we would get that acceleration is equal to, the integral of acceleration is just equal to velocity. At the same time, we can imagine v, right? If you take the integral of v, we will get the difference in v over the difference in t, which is acceleration, right? So we see here how maybe displacement, acceleration, and velocity relate to one another. We could start with displacement. We could take its integral to get to velocity. The integral of velocity would be displacement. Or of course you could go the other way around, right? The velocity, or I'm sorry, the derivative of displacement is velocity, the derivative of velocity is acceleration. We get the gist. So that is why we want to calculate the area under this velocity curve, this velocity function, because what that's going to give us is our displacement. So we drew here a line just to help us at v0, that's the beginning speed. Height is v0, length is t, area v0 times t. And now we have this triangle to figure out. Well, we know triangle is 1/2 base times height, so we have 1/2, the base is t, the height is v minus v0. Okay, so we can add them both together here, so we have displacement is equal to v0 times t plus 1/2 t times v minus v0. We can distribute the 1/2 to get this, and we can rearrange a little bit, and we get that the displacement, difference in x, is equal to v plus v0 over 2, all that times t. And that, as we can see here, is our second kinematic equation. Moving on to our third kinematic equation. This time we will have to, to rely on the first two that we have just derived. So let's just take our second kinematic equation and rewrite it up here so we can have some space. And with the first one, what we're going to do is we're going to solve for t, because we see this lone t over here. So we rearrange, you can imagine moving this to the other side, so we have v final minus v initial, and we want to divide by acceleration. So I wrote this up here, we have t is equal to v final minus v initial, all of that over acceleration. All right, so we just plug this in over here instead of our t. We get v final plus v initial over 2 is all that times v final minus v initial over a is equal to displacement. Okay, so now we would, I guess, just multiply them out, right? So now we have v final times we have v final squared minus this times this, so minus v initial squared over 2a. This is equal again to displacement. And now we should probably solve for v final, because we want it in terms of v initial, acceleration, and displacement. So we could just say, yeah, we could just rearrange this, and we could have v final squared is equal to v initial squared plus 2 times acceleration times displacement. And now we have another kinematic equation. All right, beautiful. One more to go. Now, for the last one, and the order here might confuse you. I know I said this one third, even though it says 4 here. That's just because the second kinematic equation is not really on the equation sheet, but it's still, it's very helpful. It's good to know. I want to return to our graph here, to our velocity function. And we're basically going to solve it, but we're going to remember something specific that's going to help us out. So let's just do this again a second very quick. We have this, right? This is equal to v naught times t. This is equal to 1/2 t times v minus v naught. But, so we write this down here. Remember when we said that v minus v initial is equal to, by the very definition of velocity and acceleration? Well, that's just acceleration times time, right? Because if we have the final velocity minus the initial velocity, that's just the overall velocity. That's acceleration times time. So multiplying the t by t, we just get here, again, this is very similar, but displacement is equal to v naught t plus 1/2 a t squared. And that is the last kinematic equation. Now, I want you to know that this was just, there are many ways of deriving these equations. I just, put you through one way in each. There's a lot of plug and chug techniques. I tried to use the graph. Hopefully that was a bit more visual. And the kinematic equations, why do we learn them? Why do we begin with them? Well, they're very they're very useful in that there are 4 equations and 4 unknowns, right? And each one of them relates a bit differently for variables, which is displacement, velocity, acceleration, and time. Now, of course, we know that with a system of equations, if we have 4 unknowns and 4 equations, as long as, we have 3 each time, we can solve it. If we have some unknowns, we can solve or some unknowns and some knowns, we could just solve for the rest. So these prove to be very helpful, as we will see on later. All right, it's time for us to talk about momentum. It's the next little unit we'll be going over. I'm sorry if I'm talking a bit quietly. My voice is hurting a little bit, but I've written down a bunch of notes that we're going to be going through. So I guess we start by saying that momentum is a bit different because it's not an equation that we derive necessarily. Momentum is more of a mathematical tool. It may seem arbitrary in the beginning, but it's a very helpful tool for solving all kinds of problems. Which is why we'll be going through it right now. So we begin by a definition that P is equal to mv. Notice these lines. That means that it's a vector, because mass is of course, it's just a scalar. It's a magnitude, but velocity is both a magnitude and a direction, which makes it a vector. Now, when you multiply a vector by a scalar, you get a vector, which is why P is momentum, by the way. P is momentum. So then, what can we do with this? Why mv? Well, check this out. We begin by Newton's second law, which is that force is equal to mass times acceleration, which needs a bit more explaining, because what is Newton's second law? Well, Newton's second law basically says that every force that is activated is later going to have an opposite and equal reaction. So then if I push, say, against this wall, right, I'm exerting a force on this wall. It's pushing back against me with that same force, but in an opposite direction, which is why we don't see any movement here, because I am pushing and I'm being pushed back in the same direction, in the opposite direction by an equal force and magnitude. So we have here that force is equal to mass times acceleration. That's Newton's second law. That's what he said. And we can play around with this a little bit. So if we remember from our kinematics unit, acceleration is just the difference in v over the difference in t. When I say difference, I mean delta. So we can just rewrite this as F is equal to m times delta v over delta t. Now, we can just bring the m inside the v, because m is just a scalar, right? So it won't matter. We can bring it inside the derivative. So it's equal to d or delta of m times v over delta t. But look at this. We have set in the beginning mv to be equal to momentum, to p. So we can just say that force is equal to dp over dt, right? The delta momentum over delta time. Now, what happens if we take the integral of both sides? Well, if we take the integral of force with respect to time, we can drop out this time, right? Because if we take the integral of this, it will drop out, and we get that the integral of force with respect to time is delta momentum. It's the difference in momentum, and we set that to be equal to j, to impulse. So what is impulse? What is the difference in momentum? This might be a bit hard to think about, which is why we have here a little visual. So we have here a graph which models force with respect to time. And we have this curve. Now this curve is the amount of force exerted on a system or on a body over time, or in every moment in time, right? Now, if we take the area under this curve, effectively what we're doing is we're taking the integral of force with respect to time, which we said is the difference in momentum, or delta momentum, which we said is j, it's impulse. So the area under this is impulse. Now, this leads us to our next little concept, which is conservation of momentum. It's this idea that momentum is conserved if there are no external forces acting on a system. So say we have this pen just floating here, and that is the system, and everything else is the outside. Its momentum is conserved right now until I give it a push, and it's no longer conserved. Or if it's moving right now, its momentum is conserved. Its mass and velocity is the same. But if it's moving and I give it a push, its momentum will not be conserved because it has an external force. Now, that external force, that's impulse, right? That's me delivering energy, delivering momentum into a system. So it's an external force acting on a system and changing the momentum. So, in order for the concept of conservation of momentum to be true, what we need is the sum of F external, that is, the external forces, to be equal to 0. No external forces are allowed if we will be using the conservation of momentum. Yes. And this brings us to our next concept, which is collisions, okay? How do we model collisions? We've been modeling all kinds of particles moving around, but what if there are two particles moving and they collide? What happens then? Well, this is, I don't want to say this is why, but this is where momentum is very useful for us, because we should remember that if it is a collision problem, okay, it is a momentum problem, and it is often an impulse problem, okay? So we want to look at two types of collisions, which are basically two ends of a spectrum. And in real life, these collisions don't really exist. They're more of a model, but all collisions kind of lay in between somewhere there. So it's very useful for us to model collisions as elastic or inelastic, which is the names that we give these collisions. And often, in problems, we will be asked either directly to model them as elastic or inelastic collisions, or we will be able to understand from the information given that this is an elastic or an inelastic collision and solve the problem as such. So here we go. Inelastic collisions. We've got two masses, m1 and m2, going at each other in two velocities. It doesn't really matter for our purpose right here. They collide. Now, since this is an inelastic collision, what we will see is that the two masses stick together. Okay, they stick together and they travel together after the collision at the same velocity, as if they are one mass, right? You see how over here they are separate, moving at different velocities. They collide and they keep traveling in the same velocity as if they are one mass. Now, in these types of collisions, we can use conservation of momentum. Actually, we can use conservation of momentum in both of these. But what's very interesting over here is that kinetic energy cannot be conserved, okay? And that is because, this energy dissipates into heat, right? Into deformation, so potential energy perhaps, into internal energy. If we have, the atoms moving around, into sound. And if none of this makes sense, we will be going over energy a little bit soon. So stick around and so kinetic energy is not conserved. But we can model this as energy initial is equal to, or momentum initial is equal to momentum final. So then what's the momentum of mass 1? Well, we know it's m1 times v naught, right? Plus m2 times v1. So that's initially. And that's equal to the momentum in the end, which is m1 plus m2, because they act as the same body, right? Times v final, because they go at the same velocity in the end. And kinetic energy is not conserved. Elastic collisions are a little bit different. Well, you could say they're the opposite of inelastic collisions. So let's model the same situation again. We have our mass 1 and our mass 2. They're traveling at two velocities towards each other, and they collide. Now notice that in an elastic collision, instead of sticking together, the collision is instantaneous and they bounce off one another. They produce no sound, no heat, no deformation, nothing. Just instantaneously collide. This may sound maybe a little bit unrealistic according to our intuition, but that does kind of happen, when we get to electricity and magnetism. And we should remember this is just a model, and it is very useful for us. So what happens here is that the masses stay apart. And we can still use, conservation of momentum. Since this is an isolated system, we have no external forces acting. So we can say m1 times v1 plus m2 times v1, or times v2, I'm sorry, is equal to m1 times v1 final plus m2 times v2 final. This is key. Kinetic energy is conserved. That's the difference, right? Because there's no loss to heat or to deformation or to internal energy and stuff like that, it is conserved, which is why we can use the following conservation of energy method. Now, this actually may not make sense, which is why we're going to cover energy right after we do this, but stick around and we're going to explain this right away. We can use 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared is equal the same but with final. So 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. What does this mean? Well, let's cover energy and we can find out. All right, we have laid out here energy. So we have the types of energy, and we're going to look at free body diagrams and springs at the very end. So we have a few types of energy that we should go through. The first is potential energy. Now, potential energy could be, potential energy from gravity or due to a spring. And what does this mean? It means that, how about first we go over kinetic energy? So kinetic energy, as we intuitively would expect, it's like energy of stuff that are moving. So say I have this pen and I drop it down. When it's falling, it has the kinetic energy, right, of it going down. Now, potential energy is if, say, I hold it up over here. It currently has 0 kinetic energy, but if, say, my reference is the floor, and I remove my arm, this will fall down. So it has the potential to have kinetic energy, right? Or to have energy, which is why potential energy has a lot to do with gravity, right? And with the height, if it's due to gravity. So we would write it's the mass times gravity times h. When I say gravity, I mean g. It's Earth's gravitational constant. This would be different under different, gravitational fields. And kinetic energy can be written as kinetic energy is equal to 1/2 mass times velocity squared. And we have internal energy, which is, say, for stuff like friction. Now, friction is a word we've heard, but what does it mean? Well, imagine we have a ball or this pen rolling down an inclined plane, right? If this is frictionless, it's just gonna, roll right down. And yeah, it'll just roll right down and there'll be potential energy because, right, it's up, and there'll be kinetic energy because it's rolling down. But if there's friction involved, then the friction is actually going to place a force on this, on the pen. Now, this is more easily imagined with, say, a box, because there are 2 types of frictions. There's the static friction and kinetic friction. What does it mean? Well, imagine you're trying to push a box, a heavy box. So you push it until you manage to make it move. So why would I move in the beginning? Well, that's because there's a force in the opposite direction that you're pushing on it because of Newton's second law, right, if we remember, which makes it so that you're not able to move it until you push with enough force that you overcome that friction, the static friction. But then when you manage to push it, it's not just going to, slide without you putting in any work, exerting any force on the object, right? You need to keep pushing it, but it's easier than it was before. That's because now you're overcoming not static friction, but kinetic friction. So kinetic friction is less than static friction, and we can model friction as, energy internal is equal to the force of friction, right? Static or kinetic, times the distance that this object has traveled or the system has traveled. Now, over here I have a person pushing a box of mass m, and you can see that the force applied is going to the right and friction is going to the left. Now notice that I have two more arrows, and that's the force going downwards, mass times gravity. What does that mean? Well, that's the weight of the object, right? It's in the downwards direction. And the natural force is perpendicular to the surface. The natural force, that's just what it is, right? It's like if I push this wall, it's going to push me back with an equal in magnitude but opposite in direction force. Same with the box. The box is pushing down the ground, so the ground is pushing up on the box, and that's the natural force. So what is the force of friction? Well, force of friction is equal to mu, which is the frictional constant, times the natural force. And yeah, there we go, right? That's friction. That's friction, that's internal energy. Now, there's this idea of conservation of energy, which is very important, which is that energy can't be destroyed and can't be created. It can be converted to different forms of energy, though, right? So you can't just create energy and you can't destroy energy, but you can convert kinetic energy into heat energy, into sound. You can convert potential into kinetic. You can convert kinetic into potential, but you can never destroy or create energy as long as the system is isolated, which means that the energy initially will be equal to the energy in the end of whatever happened. That's a very helpful mathematical tool. We can tell ourselves that if the energy internal is equal to 0, that is, there's no friction because that's an external force, and there's no air resistance or something like that, then the difference then energy initial will be equal to energy final. So then we can write this differently as the difference in potential energy plus the difference in kinetic energy is equal to 0. Or, of course, the difference in potential energy is the negative of the difference in kinetic energy. That is, one is converted into the other. So now, what does springs have to do with this? Well, springs have a K constant, first of all, just like, friction. And we can compress them. And what we're doing is we're creating potential energy because the spring now can decompress and push the object, cause it to have kinetic energy, say, right? And this is also modeled by 1/2 K times x squared. And x, of course, is just the displacement of the spring from its natural state. All right, well, we've done the theory, right? We've done the theory that we wanted to cover, that we need this time. And, I think, Mr. Paviko said this once, and I thought it was very, it's insightful, and I keep it with me that, and I might have already said this in a previous lecture, but, you can learn a lot of. So then I'm holding here just a piece of paper that shows us what the problem that we're going to be solving today. And it says, first of all, we have this picture of a spring that's been stretched. We can see a distance d, and there's this pan that's hanging over it, and there's this mass and height. Let's see what they're talking about. So, an ideal spring is hung from the ceiling, and a pan of mass m, big M, is suspended from the end of the spring, stretching it a distance d, as shown above. A piece of clay, also of mass m, so these are the same mass, it's both capital M, is then dropped from a height h onto the pan and sticks to it. And they ask us to express all algebraic answers in terms of the given quantities and fundamental constants. All right, so the first question is to determine the speed of the clay at the instant it hits the pan. All right, let's get some fresh paper and we can start solving it. All right, we've got a new paper, and if you see me look to the side, it's because I'm looking at our lovely question right here, because we will want to draw this out. So we have a spring here. That's its natural length. And it is stretched a distance d by being attached to this container that's connected to a mass m. And there's a little piece here. It's also m. So we've got, this is a distance. What's the distance? Distance h. And the stretch over here is a distance d. This is not a zero, by the way. This is a mass. Let's see if we got that correctly. It seems that we did. Okay, and they are asking us to determine the speed of the clay at the instant it hits the pan. Okay, so the clay just falls onto the pan. We need to figure out its speed. It seems we're just going to be using, well, just our simple kinematic equations for this one. So which one would we want to use? Let me actually pull up our kinematics. So we've got this. What do we know? We know our height. So we know our distance of x. We know gravity. They're asking for our final speed. Yes. We know the initial is just 0, right? So I think we're going to use this equation, equation number 4, and solve. So, yeah, let me grab my calculator also. All right. Well, this is actually not going to be d. I got confused because it's h is the distance. So this is not going to be d. This is going to be h. But that is our final correct, hopefully, answer. And it is because it should be. All right. Let's move on to question B. What are they asking us in question B? Let's take a look. They want us to determine the speed of the pen just after the clay strikes it. Okay, so what do we have here? We have a collision, right? Now we know that collision, we're going to be using momentum. We might be using impulse. So they're saying that the clay was going to fall down at distance h. It's going to hit the pen, and they both have the same masses. And we want to determine the speed of the pen. All right, so the speed. Speed, remember, is magnitude, so we don't need to worry about direction. How do we go about this? I say we use our momentum equations. So let me pull out our momentum notes a second, and we're going to take a look at that. So then what we have here is, as we've looked at before, conservation of momentum, because the force external is equal to 0. So there's no impulse, and momentum is conserved. So we can say that momentum initial is equal to momentum final. All right, let's do that. So P initial should be equal to P final. So what's the momentum initially? Well, the momentum initially, we have the pan that's not moving at all, so that's just 0. And we have the mass in the air here that's definitely moving, right? It's falling down. So then we said momentum is m times v, right? So we have initially m v is equal to, that's initially, right? This is one. Finally, we have they're both moving, so they both have momentum. And, well, if it's right after the collision happens, these two are going to be together, right? Because they ask, determine the speed of the pen just after the clay strikes it. I'm reading off of the problem here. Which means that we can effectively say that this is like an elastic collision, even though we don't know that quite yet. But at the moment, it is. Like at the moment of the collision, right after the collision, we can say, yes, this is kind of like elastic. Which means that these two are going to be the same mass. So we have, right, that mass plus that mass. Because remember, they're the same mass. They're equal. Right? All of that times v. What v is it going to be? Well, it's going to be v final, right? Because that's after the collision, right after the collision. They're going to have the same velocity. Now, they may have different velocities after the collision, but right after the collision, they're going to have the same exact velocity. So we can say v final. Okay, well, we can solve this because, first of all, what we're looking for is, let me check one more time. Determine the speed of the pen just after the clay strikes it. Okay, well, let's collect together terms. So we can say mv is equal to 2m v final. But we know that v final is that, so we can cancel out an m over here, right? And we can say v is equal to 2 times 2g h. And let's see now. Well, that's just our final answer right here. We have the v. Now, what I got confused here, this is not the v initial. This is also v final, but of only the pan, right? So this is our answer right here. We have just answered b. Now, this one was a little bit of a confusing one, even though we see we've done it in very little rows, because we need to kind of understand. They're asking us for what is the speed of the pan right after the clay ball hits it. Does that mean it's v initial? Is it v final? Okay, it's v final, but it's probably only 1/2 v final, right? Or is it maybe double v final? So it's confusing, and we should always, try and conceptualize both the situation, what's happening of the clay ball hitting the pan, but also we should try and visualize what they're asking us. Because often it's not just a plug and chug question, and we need to use more conceptual understanding, conceptual thinking to just think through these problems and come to a solution. All right, let's see what's next. All right, so next up, we have a bit of a more challenging question because, I'm sorry, they're asking us to determine the period of the simple harmonic motion that ensues. Now, I purposely didn't introduce simple harmonic motion yet because I think this was helpful, solving these problems before we get into that. But we can go over it now very quick. So, simple harmonic motion, what is it? Well, this is a bit of a new concept because it's a completely different, different unit, different chapter, different kind of section of the physics textbook. And imagine I'm holding a pendulum, okay? So we have a mass at the bottom, and there's a string. And this mass, I pull it up, and I let go. What it's going to do is it's going to swing back and forth, just like that, right? Now, when observing these types of systems, we can come to, we see very interesting phenomena. So, for example, the period. What is a period? A period is how long it takes for it to do a revolution, right? Frequency is just the reciprocal of that, which is how many revolutions, how many periods does it go through per second or per unit time. So what we see is that the amplitude. What's the amplitude? The amplitude is, if this is our axis, how far up does it go? Right. So you could have an amplitude over here. It oscillates like this, or you could have a period way up here, and it goes like that. So then what we observe is that the amplitude is independent of period. It's independent of frequency. That is, it's going to move at the same, time. So it's going to move at different speeds. And then we relate all of these different, sort of, I don't want to say characteristics, but all of these different, like all of these different parts of the system. What we see is this very interesting equation that we can model. So let's write this down up here. What is this? That is also, I guess, something that we have not really quite covered, but we don't need to right now. Just rest assured that it's speed, but in rotational units. Now we don't need it, so I'm just putting this here because that's also another thing that's equal to, but check this out. This is equal to 2 pi over our period, which is equal to 2 pi frequency, right? Because it's just reciprocals, which is equal to mass over k square root, which is finally equal to gravity over length square root. Now, some of these are going to be new. Some of these constants we've already seen before. Don't get scared by the ones that we haven't. That's just because they're going to be not important to us right now. But I'm putting them there just so you know that they exist, so you can, so you won't be surprised maybe next time that you see them. What do we already know? Okay, we don't know this one. We do know period, we just talked about it. We know frequency. We know mass, right, of course. K, we do know K. K is a spring constant, right? And gravity we know, length we know, but we're not really dealing with gravity and length right here. I mean, we're dealing with a spring that should have a K constant. Matter of fact, do they give us this K constant? I wonder. Suspended from the end of string, stretching. They don't, but we could probably figure it out from, just the quantities that they give us, right, and the fundamental units that they give us. This is, again, not notes for me. This is just the question. So then I say that with this, I think we can start and solve this problem. All right, let's try it out. C. What are they asking us? They're asking us to determine the period of the simple harmonic motion that ensues. All right, let's do it. Period. So let's rearrange this a bit. We're going to use these two, right, because that's what we want right now. So with a little bit of rearranging, we get that T should be equal to 2 pi times the root, and because we took the reciprocal, what we're going to want to do is we're going to want to switch these up. So we're going to have K on top and mass on the bottom. But my friends, I've paused the video just to make sure that I'm doing all of this correctly, and oh no, we have made a little mistake, and that's just with the reciprocals, because over here, this is not m over k, this should be k over m, so we're just going to make a little arrow that shows that, and here as well. So I'm sorry, we made a little bit of mistake, but this is the square root of k over m, and this is the square root of m over k. Again, we didn't change any of the math, but we're just changing the position of these just because I made a little error. But here we go. All right, next up. All right, so let's start to put in our variables and numbers here. So it's equal to 2 pi times, what is m? Oh, well, we know what m is. M is big M from the clay ball plus big M from the pan, so that's just 2m, I'm going to square root all this, over k. Now what is k? I don't know. Let's try and calculate what k is, right? So k, we know that the force of the spring should be equal to the k constant, right, times displacement. Displacement I'm writing in d because look, we know what displacement is. Displacement is just d. So we can solve for k by saying that k is force of spring over d. Well, what's the force of spring? I know what the force of spring should be. It should be mass times gravity, right? Because look at this. We can make a little free body diagram. So we can make a little free body diagram of our mass. We have our mass here, held up by a spring, right? So then we have mg going down, right? And we have force of spring going up. And these can't balance each other out at a distance d. So this means that we can just plug in over here for force of spring, mass times gravity. All of this over d. Okay, so we can put this k back in here, right? So we have mg over d. Okay, let's simplify this a little bit. So we're going to go back down here. Period is equal to 2 pi times, oh, look at this. M's cancel out. We can bring the d up front. So 2d over g. There we go. That should be our final solution for the period. Beautiful. All right, on to D and E. These last two are actually going to be easier. So we can write where we were at D right now, and they ask us determine the distance the spring is stretched from its initial unstretched length at the moment the speed of the pen is a maximum. Justify your answer. So let's think about this conceptually for a second. When it comes to simple harmonic motion, when is the mass at its, greatest speed? Well, it should be in the middle, right? Because when it goes this direction, it slows down until it comes to a rest, and then it goes in the opposite direction, and it's really fast, and then it slows down, right? So it should be at the equilibrium point that the v, or the velocity, is at its maximum. In that case, what we should do is we should set this up, right? This is a spring, so we can just say that the k, right, the spring constant, times x, which is what we're trying to find, that's the distance in which the v will be maximum, should be equal to, the forces. So it's just going to be 2m, because we have two of the masses, times gravity, right, because that's what's pulling it down. So then we can just plug in the k here, which we found to be mg times d. So over d, all this times x should be equal to 2mg. Oh, but look at this. The m's cancel out. The g will cancel out. And we're left with x over d is equal to 2. Therefore, x is equal to 2d. That is where Vmax, that's where the velocity will be maximum, at 2 times the original displacement. That makes a lot of sense, right? Because we have double the mass. So we could have even skipped all of this. Anyways, on to our last question, question E. And they say the clay is now removed from the pen, and the pen is returned to equilibrium at the end of the spring. A rubber ball, also of mass m, is dropped from the same height h onto the pen, and after the collision is caught in midair before hitting anything else. Indicate below whether the period of the resulting simple harmonic motion of the pen is greater than, less than, or the same as it was in part C. So what they're saying is that this collision is going to be an elastic collision. Yes, or at least it's not going to be inelastic because the two don't stick together. Well, it's actually even simpler than that. Scratch what I just said. All we need to know is that there's less mass. Therefore, the spring will be less stretched, and the amplitude will be greater. So they're asking us for the period. The period is actually independent of the amplitude. So we're going to need to think about this a tiny bit. But I'm inclined to say less than. Let's pull up our notes and we'll see. Well, as I was pulling out our notes, I actually noticed that our notes are right here, right? Let's rewrite this again. T is equal to 2 pi mass over k square rooted. Well, if mass goes down, then T should go down, right? Because these are directly related. Therefore, the answer is less than. And there we go. That is our FRQ solved. And we have put, all the stuff we learned together. And thank you for watching this lecture. I hope this was helpful.